Today I'm going to talk to you about graphs of logs. To begin with, I've drawn the graph on GeoGebra of a log to the base 2 of x. Let's just have a look at some of the key features for this graph. You can see first of all that the x-intercept is 1. And let's look at the reason why that would be. Because this is the graph of log 2 to the, it's base 2, when x is 1, y is always 0, and we know that because 2 to the power 0 equals 1. And don't forget, we're looking at the inverse operation. Now, one interesting fact that we could do is to compare what we already know. We've already studied index graphs. So if I plot the same base, so y equals 2 to the power x, we can have a look at that relationship. Now, I'll just get rid of the keyboard there. We can see that there appears to be a reflection. So the red graph here is y equals 2 to the x, and this grey graph is y equals log to the base 2 of x. Now, if I was to just confirm that, I'm going to just put the line of y equals x in there to show you the line of reflection. We can see that that's our line of symmetry. And you can see that the distance at each point away from each point on either graph is equidistant. So we can see it's clearly a reflection. So let's recall some of the properties of the exponential graph, the y equals 2 to the power x graph that we've studied back in Unit 1. So I've got the graphs written up here. Let's have a look at some of the relationships that we've studied. So we know that the domain of our y equals a to the x, so obviously I've looked at the base 2, is real numbers, and the range, that's the y value, is all positive values, because if we have a look at this graph, there's an asymptote along the y equals 0 line, and that's the x-axis. So that's an asymptote. If we look at a to the power 0, so when x is 0, we can see that y is 1, and that shows us our y-intercept here. And if we have a look at what happens as we tend towards negative infinity, we can see that it just gets closer and closer and closer to that x-axis, but it actually never ever reaches it, hence the asymptote. And then if we look at the the log graph, if we have a look at what happens when x approaches negative infinity, well, we can see on this red graph here that in fact it never ever touches the y-axis, it never ever crosses that y-axis. So we can say that x equals 0 is in fact an asymptote of this log to the base 2 graph. Let's have a look. I think I've already explained that we know that anything to the power 0 is 1. So obviously, just looking at the reflection, we can see that log to the base of 2, log to the base 2 of 1 is 0. So that's our x-intercept. Looking at the range of this graph, we can see that it goes positive, real numbers are positive, and we can see that okay, so I've actually formalised those properties of these graphs, but actually what we want to try and do is actually look at the graph of y equals e to the x and its inverse, the natural log of x. And as you can see, remember e is just a base. E is actually a number greater than 1. We know that e is roughly 2.17, etc., etc. And there's the natural log, which is inverse. And we can see the same properties exist. We have the y equals x line is actually the reflection or the line of symmetry. And of course, the key features for the natural log of the base e of x is exactly the same as the natural log of x. So that's great. Now what we want to try and do is study some transformations of these graphs of log to the base a. So log to the base e, don't forget, is the natural log of x. I've just repeated myself. So let's have a look at how we might sketch. Now what I want you to remember is that we use the same transformations as before. So we've done transformations of graphs. When there's a value in front of the function, that's our dilation factor. When there is some kind of transformation in a bracket, so if it was a plus or a minus, so in this case it's not, but say it was x plus 1, we know that's our horizontal shift. And if we were to have a plus k value at the end, that would be our vertical shift going up and down. So we just need to remember what our a, h and k do, and link it to these properties of these graphs. And of course, whenever we're sketching a graph, we do need to remember to put the key features in, like the x-intercept, the y-intercept, and for this particular graph, any asymptotes. We should know the shape of the graph. So as you can see, the log graph goes like this. That asymptote is very important. So let's do some examples. I'll write them down. So let's do the x-intercept first. So we've got 0 equals 3 natural log of 2x. Now, if I divide by 3, I'm still 0 equals the natural log of 2x. I'll just remove those brackets for a moment. Now, I'm going to use my equivalence formula, so don't forget just up here it's e to the x equals y is equivalent to writing the natural log of y equals x. So I'm obviously going to write it in this form here. So that tells me that e to the 0 equals 2x. So therefore, 1, because remember anything to the power 0 is 1, is 2x. So if we divide by 2, x equals half. So our x-intercept is a half. Looking at our y-intercept, now if we actually look at this function here, there's no horizontal shift, and our properties of the log graphs, if we just scroll up, we can see that because there's no horizontal shift, we're going to have this asymptote at exactly the same point. So the asymptote for that will be at x equals 0. So I'm just going to write not applicable here because we've just discussed it, and therefore the asymptote here will be x equals 0. So when I sketch it, same shape, and we've just got the x-intercept and there's no y-intercept there. So sketch a graph, we just put some axes in. Doesn't have to be the full axes, but just for the purpose of this video, I'll just put that there, cut it like that, it's facing that way, and label my x-intercept as 1/2. You can put a coordinate on there if you like. You can put 1/2 0 there, but that's absolutely enough we need to do. Just put that asymptote on there as a dotted line normally, but clearly because it's the axes, I'm just going to write x equals 0. Oops, apologies.